Okay, let's return to a probability experiment that you've seen before, and that is flipping 3 coins. Recall that the sample space for flipping 3 coins would be as follows. Suppose that you flip all 3 heads, there would only be one outcome like that. If you flipped 2 heads, then the 2 heads could either be the first 2, the last 2, or the outside 2. If you have only 1 head, that head can only appear in one of the 3 places. And of course, if you have 0 heads, we have tails, tails, tails. And that's a total of course, 8 outcomes. Suppose that we are specifically interested in the number of heads generated from each one of these 3 coin flips. So what does that mean? That means for each one of the outcomes here, we are going to get a numeric value that represents the number of heads. For example, let's just create like a little row here of results. So if I flip 3 coins and I get triple H, then how many heads are there? There are 3. If I have the next 3 outcomes here, this one, and this one, based on how I created the sample space verbally, each one of these represents 2 heads. And each one of these represents 1 head, and the last one represents 0. So again, these are all numeric values that represent the variable number of heads. Any time that we have a function or rule or variable, whatever it is, anytime that something like that assigns a numeric value to every single one of the outcomes in a sample space, we call that a random variable. Random variables are usually represented by capital letters such as X, Y, or Z. So in this scenario, we could hypothetically call the variable X being the number of heads. While a capital letter such as X basically is our random variable itself, its lowercase counterpart usually represents possible outcomes of that random variable. I'm just going to use RV for random variable. It makes things short here. So what does that mean? That means in our scenario here, put an arrow here, what are the possible outcomes of our random variable? We can clearly see that our lowest number is 0. We have 1, we have 2, and the highest number we can get is 3. Each one of these numbers represents how many heads you can have when flipping 3 coins. This also allows us to create a probability distribution for our random variable. If you recall from the probability chapter, we talked about probability distributions and how that each probability has to be between 0 and 1, and the sum of all the probabilities has to be equal to 1. Well, let's go through that and make sure that's good. So if we want to create a probability distribution for all the values of X, then we have to list them out. So 0, 1, 2, and 3. So right away, we're looking at this and saying, well, what's the probability that we get 0 heads? Because remember, that's our random variable right here. So we go over here and go, well, 0 heads is this one outcome out of a total of 8 of them. Now, if this was an unbalanced coin and it wasn't a 50-50 flip, there would be more at play than just what we're about to do. But because it's 50-50, each one of these outcomes is equally likely, which means this is only 1 out of a possible 8 outcomes, and that's your probability for getting 0 heads. Just like if we jumped over to the other side, what's the probability for all 3 heads? Also 1 out of 8. And then each one of these having 2 heads or 1 head are all 3 outcomes out of 8. So if you look here, you can clearly see that each one of these probabilities is between 0 and 1, and the sum of them, 1 plus 3 plus 3 plus 1, 8 out of 8 is going to give you a total of 1. So this is our probability distribution for this random variable, which represents the number of heads. The last key element here returns us all the way back to the beginning of the course, where we talked about the difference between discrete and continuous variables. So just as a reminder, discrete versus continuous here. Just as a reminder, whenever we're dealing with a discrete variable, we're talking about countable values, whereas continuous basically could be any numbers on a number line, including decimals. So if you look at our outcomes specifically for flipping the coin, these are clearly non-decimal values, counting numbers basically. So we would call this a discrete random variable. So this would be a probability distribution of a discrete. Again, we'll call it RV for random variable. Let's look at another scenario, and for that we're going to chat about the US Census. So when that is sent out, usually on it there'll be something about family demographics, and you'll basically talk about, who's in your family, the guardians, the children, gender, whatever it is, right? So let's just say that we decide again to assign a value, some number, to the number of inhabitants per household. We again are going to call that the random variable x. Just like last time, we should be able to assign outcomes to that. So if you own a house and live by yourself, that's 1. Let's say it's just you and your significant other or somebody else, that's 2. This could go on for almost ever, but as you go through the census scenarios, it's limited in what you could end up with. What I did for this scenario is I basically made it 1, 2, 3, 4, 5, 6, and 7 plus, but I just assigned the number 7 to 7 plus because there's going to be so few that are more than 7. I just sort of use that number generally. So suppose all of that data comes in and a probability distribution is generated for this random variable, which obviously must be discrete because we're talking about countable data right here. And we end up with this. So for example, there is a probability of 0.267 that the person is living alone, and so forth throughout this table. If I'm working in the government and the census data has been provided for the, again, number of inhabitants per household, I would think the first thing that they'd be most interested in is the mean number of inhabitants per household. So in other words, what's the average number of people that will be in a home in the United States? So our focus now shifts to how to find the mean of a discrete random variable, and luckily enough, we actually have a formula for that. So let's break it down. So clearly we have mu meaning mean, but this little variable here is an identifier. It just basically says mean of the random variable x. That's all that's saying. We know that this is sum of. We know that x, remember, are the possible outcomes. And remember, the I means that many different outcomes are going to show up in this variable, and that is evident by, again, the summation sign. And lastly, this is the probability of the outcomes. So altogether, what is this saying to do? Well, remember we work inside out, so we're going in here first. So according to this, They want us to multiply every value of x by its respected probability, which is pretty logical because what it's doing is it's giving that number a weight in a sense. So 1 has a 0.267 probability of occurring, so we want to give it a little bit more weight than, let's say, 3 that only has a 0.158 probability of occurring. So again, we're going to take every x and multiply by its probability, and then when we're done, all we're going to do, ta-da, is sum them all up. Sounds a lot like some of the previous stuff we did in terms of standard deviation. This is going to be a little bit easier because if we are, again, maybe creating a new column here, then all we need for that column is x times p of x, and we will be off to the races. Okay, so again, what are we doing? We're basically just multiplying these columns. So 1 times 0.267 is, of course, just 0.267. And then we have to do 2 times 0.336, which is going to be 0.672. And then 3 times 0.158, which is going to be 0.474. I'm just going to pause real quick to fill in the rest of the table. Okay, as you see, everything is now filled out. This column represents the product of the first two columns, and obviously the main component of our formula, x times p. So what is the goal? Well, according to this, all they want you to do is find the sum of this column based on our summation symbol, and that should give us 2.525. And what does that mean now? Well, that again is the mean of our random variable x, or in other words, this is the mean number of inhabitants per household. Okay, this number should make a little bit of sense as I show you its placement in the actual outcome. So remember, when they send out the census, they're basically going to be getting just these numbers coming back, either 1 or 4 per household, 7, whatever it is. So 2.25, which falls basically between these two numbers, ends up being the mean of these values. So obviously, it's maybe you might look at this and be like, oh, well, 4 is the average because it's this number that's dead center in the middle of all these. If you add them up and divide it by, I get 4. The problem is that the probability is weighted heavily towards the top. If you look at the bottom numbers, they are much smaller, which means these numbers are a lot less likely than these. So our mean is going to be dragged in this direction away from 4 and more towards the upper numbers. It turns out that it's going to fall somewhere between 2 and 3, about halfway, at 2.525. Generally, we use the term mean for a discrete random variable when we're dealing with collected data that we're trying to analyze. It turns out that in the world of probability, there is an equivalent term called expected value. We tend to utilize this term to describe a discrete variable and its mean whenever we're talking about theoretical long-term probability. So let's see what that looks like. It says a life insurance company will sell a $200,000 one-year term life insurance policy to an individual in a particular risk group for a premium of $195. Find the expected value to the company of a single policy if a person in this risk group has a 99.97% of surviving 1 year. The focus of this problem is all about the company's profit. The company wants to know whether this life insurance policy is a good thing for business, basically. Just like we did for previous problems where we had a probability distribution that we could manage, this time we're actually going to be generating that probability distribution based on the given information. So profit is going to be our random variable x, and we're looking for the probability of these profits occurring. So what are the scenarios? Well, person lives or the person doesn't live. So let's talk about that. So if we look at our problem, it looks like the company is selling this insurance policy for $195 for a year. So that means if the person lives, then the company makes $195 because the person is paying that to them. Okay, but what about if they don't live? Well, the whole point of an insurance policy is the payout if they don't live. So that means $200,000 is going to be given out to the policyholder if they don't make it through the year, so to speak, right? But it is worth knowing it's not just $200,000 because the people have already the person has already paid for the actual policy. So this value here is going to be the $200,000 less the initial $195 that was paid for the plan. So that's going to end up being $199.805 that is going to end up being given to the policyholder. But the key thing here is that this is in terms of profit, which means the actual insurance company is losing that money when they're giving the payout. So this is actually a negative. Lastly, what are the probabilities of these options? Well, you were given one probability here, 99.97%, and this is the chance of survival. In other words, we're in our lives column, so it's a 0.9997 probability that they live, which means it's a 1 minus 0.9997, i.e. the complement, that they don't live. So that's going to be 0.0003. Okay, so what's the focus now? We want to find the expected value of this company's profit, which is our random variable. Another way to say that is expected profit. And as mentioned, expected value is the same as mean of a discrete random variable. So we're just going to be using this formula again, this highlighted formula. That's it. That's the goal. So we're going to go down here. We're going to use that exact formula, but we're going to use a different variable to begin it. So we usually say mean of x, but the equivalent to that is actually e of x, which is going to be, I'll write it up here, the expected value of x. So these basically are the same thing right here. It's just a different way to write it. Therefore, we can just go back and use the formula for, highlighted formula here, for mean of a discrete random variable. So what did we do before? We basically just took every outcome for a random variable x and we multiplied by its respective probability. Same thing goes here. We need to take every outcome and multiply by its respective probability. We're going to get all of those products, and then we're just going to add them together because of this guy right here. That's our goal. So just as an aside, in our previous examples, when we were finding the mean of a discrete random variable, which would be here, what did we do? We created this new column and did all the work, and that is perfectly fine to do. But the reality is we only have two elements here that we're dealing with. We got this guy and this guy, both columns. So we could just literally just multiply each and add them in one row. It just depends on what you want to do. So what do I mean by that, by the way? So if I was to take my first x and multiply by its probability, it would look like that. And then if I was to take my second x with the negative sign and multiply by its probability, it would look like that. And this is exactly, by putting the plus sign between them, that's exactly the mean of a discrete random variable. We're adding the products. We could just do this really quickly, and we would end up with $135. So what does that mean? That means, and by the way, this is positive. This means that every year the company is making $135 on this insurance policy plan for only one person. So they are making a nice profit, especially considering when you might have thousands or tens of thousands or more people that are actually signing up for this plan. Yes, it's possible that somebody might not live and you might end up having to pay it out, but in the long run, which is how we mark out and forecast business models and such, they are making a profit, and that is what matters. So we've covered everything in terms of the mean of a discrete random variable, but it turns out whenever we actually have a mean of something, standard deviation is not too far behind. So that's where we have to go with this next. Let's look at the formula. So it turns out that there's actually two different formulas here for finding the standard deviation of a discrete random variable. It just depends on the textbook, which one that they prioritize. This is more of the theoretical formula because it does a really good job of mimicking the standard deviation formula that you're more used to from the class, which is basically taking every value and subtracting the mean, squaring it, and so forth. Obviously, there's no dividing by n minus 1 here, but the numerator is the same, and then basically multiplying by the probability to get its weight. Now, we can absolutely do that. It just takes longer. So I tend to sort of go on the side of what's called the computing formula. The computing formula is made so that it's easier to get through in terms of finding the results. It's great for student use. So we're going to prioritize that and a lot of the same types of computing formulas going forward. All right, so let's look at the formula and see what we need out of this. Well, you can clearly see that in the middle of this, very different than over here, you basically have to square x and then multiply by the probability. So in our previous scenario of the mean, we had to multiply by just x by its probability, right? So here it looks like we have to square x first, which means if we're going to do this with the column method, that's probably the first thing we want to do, is find all of the x squareds. So take everything in this column and square it. So we get 1, 4, 9, 16, 25, 36, and 49. Next, it looks like we then need to take that same x squared value and multiply by the probability of x. So in other words, we have to multiply these two columns times one another. You can see the first one's going to be very simple because it's just 1 times 0.267. But then the math starts getting a little bit more involved. It would use a calculator. So I'm going to pause the video and just write them all down for you and be right back with you. Okay, so I'm right back with you. I've listed out all my x squared times p of x's. So our goal here, based on the formula, is to find the sum of all of these. Just as a reminder, in case I let this in my brain slide, remember this is the same problem that we saw before, where random variable x equals the number of inhabitants per household. And remember, we also found the mean about, several minutes ago. So what do we need to do here? We need to find the sum of this column. If you do so, we're going to get about 8.399 as our result. So 8.399 is basically going to replace this entire piece in the formula, just like similar to the standard deviation calculations that we've seen before. It just replaces the summation where it is. So what we can do now is we can go down here and we can actually do this. So let me throw the equal sign in here. Let's get my square root going. So we can take our 8.399, replace the highlighted version here, and then according to the formula, we have to subtract the mean squared. But we already calculated the mean of the inhabitants per household earlier. That was found right here at 2.525. So what we're going to do is we're going to throw that into the formula, 2.525. Remember to square this first and then subtract from 8.399. That'll give us the square root of 2.023375. I purposely went to many decimal places so that I eliminated as much rounding error as possible. Also recall that anything in the square root when dealing with a standard deviation is always going to be the variance. They didn't ask for that, so we don't need it, but I wanted to make sure everybody remembers all that good stuff. And if we calculate this, we are going to get 1.4222 as the standard deviation of the discrete random variable.